I'm going to explain the wave on or the wave speed for a string or spring or whatever equation. It says that the wave speed, if you were to cause a wave in a string, would be equal to the square root of tension over the linear mass density, which is just m over L. I'm not going to derive this because, one, I actually don't know how to really derive this equation, but also most AP Physics students are never going to ever need to do that. So thought I'd at least physically explain why tension is related to wave speed, why linear mass density is related to wave speed. And it all has to do with how the particles of this string, I will always mix them up, how the particles are moving. So hopefully you kind of understand that for a transverse wave, the particles in the spring are moving perpendicular to the direction of the wave. So common misconception is that, hey, your like particles on the string are moving that way, because it kind of looks like that, right? Like this wave, it'll literally look like it's moving that way. But that's just an illusion. Really, the particles are moving up and down. I mean, think about it. In order to create this wave, what I would have to do is I would have to move like this particle up, and I'd have to move it like so. And then what would happen is over time, once I start pulling this down, this piece of string, or I guess the particles up here, would be causing these particles to begin to move up. That tension is physically causing it to move up. And as I start bringing it back to equilibrium, these pieces of the string are moving the top of the peak back down to equilibrium. So all of the particles are just moving up and down, caused by the tension within the string. So hey, that kind of hopefully should like help you see that relationship. If the tension in the string is stronger, these particles, right? So think about like, so if I have a wave, right? Let's say I have a wave like this. These particles are going to, right? If the tension is stronger, the force that's going to bring these particles up so that you get like this next part of the wave where these particles have moved up from equilibrium, that force is stronger. And the force that is going to be bringing these particles back down to equilibrium, tension is stronger. So the tension is a driving force that is moving these particles up and down back to equilibrium. If you get more tension, these particles are going to be accelerating quicker or at a faster rate. They're going to be accelerating at a faster rate due to Newton's second law. The wave itself will be moving a lot faster. It can travel a lot faster. And you can connect Newton's second law back to mass per unit length. So the deal is, when you're dealing with these little amount of particles, you're really looking at that like a really small amount of section per unit length. So, for example, if I were to look at this section, right, analyzing that small section with a small amount of distance, well, if my mass per unit length were smaller, what that means is, for that same distance, let's say this is a big mu, and let's say this is a small mu. For that same distance that I just measured right here, since L is the same and mu is the same, or not, well, this is like the L of the total thing. So what I really mean is mu, so okay, it's a proportion. So M over L would end up equaling, that ratio from total mass to total length would equal the ratio from a little amount of mass to a little amount of length. And I'm just using D to show that I mean little. So dm over dl, if I were to use, if this ratio is smaller, that means for the same amount of length, there's less mass. Hopefully you can see there's less mass for the same amount of tension. There's going to be more acceleration, and your wave in general will be moving faster because everything is accelerating quicker. If you have the same length but more mass, then that means that ratio is larger. So if you increase the mass, there will be less acceleration going on, and the particles won't be able to easily move back to equilibrium. It's all about equilibrium. And in fact, when you have a simple harmonic oscillator that is causing the wave, for example, if I was if I had like a spring, let's say, how do I do this? Let's say I had like, you know, here, let me use I need to get new markers. That's one thing I gotta do. But what I'm trying to say is, if you, let's say you had a block like so, and I pressed it down a small length, and I had like a string attached. As that block moves up and down, it would create like a sinusoidal wave, right? If you have a simple harmonic oscillator. And this would be a simple harmonic oscillator. You can do the proof. Gravity, won't change that scenario. It's just a spring. KS, right? Linear restoring force. Simple harmonic oscillator, you get a sinusoidal wave. The speed of that wave is not determined by the frequency at which you oscillate this thing. It's determined by the tension, what's like holding it back, and the mu. Hopefully that makes sense. You'll always have a little bit of tension, because if you had zero tension, I'm pretty sure your rope would just disintegrate. So, you'll be able to create waves most of the time. You'll never have zero tension. Otherwise, if you had zero tension, when you move the rope up, it would literally like disintegrate. So there's always going to be tension, right? Tension is a thing moving it up. So hopefully that makes sense. Hopefully that isn't a too foreign of a concept. Thank you for watching. Have a good rest of your day.